G'day chemistry students. In this video, we're going to be looking at some spectroscopy techniques to test the concentrations of different inorganic samples using what we call a calibration curve. Let's get into it. So for this particular technique, we're going to be using UV Vis spectrometers. Very similar to, say, an IR spectrometer in the sense that we have a sample, something that's sitting in the middle. You might be able to see sort of where the containers are loaded in. And in that sample, we're going to be passing UV or visible light into it. Those samples are going to resonate in some way, shape, or form, essentially absorb the light. And we're going to be able to take measurements of what kind of wavelengths have been absorbed by that substance, as well as the amount that has been absorbed by that substance. And in particular, how much UV or visible light is being absorbed by the substance is going to be the factor that allows us to determine the concentration of the sample that we're looking at. So first off, let's just talk very broadly about UV Vis spectrometry and what the machine actually does. Similar to IR, we have a light source. Instead of it being infrared light, we're instead going to be using UV and visible light. We can have something that disperses, what we call a monochromator, something that can split the light up and allow us to have one color at a time, one wavelength at a time. So we can go from blues to greens to yellows to oranges to reds, etc. Let all of those wavelengths through one at a time and figure out how much, if any, light is actually being absorbed by the sample. It then goes into a detector to be able to give us our spectra. This is an example of what a UV Vis spectrum might look like. We have a y-axis which indicates how much light has actually been absorbed, and then as we go across our x-axis, it's showing us the absorption of light at our different wavelengths. So when comparing UV Vis and IR and UV Vis are both good ways of measuring how chemicals react with different parts of the spectrum. Infrared light is measured through transmittance, so that's why we saw troughs in our IR, because what the graph is generally showing is how much went through. Essentially everything has about 100% transmittance unless something's been absorbed, and that's where we see a big trough drop down. But for UV Vis, we usually measure by absorbance, so how much was taken in. So low absorbance means pretty much everything went through. High absorbance, or an actual peak, indicates that at least some of that light was absorbed by the sample. Going all the way back to our resonance concepts, which you've looked at a few times, different types of substances will absorb different parts of the spectrum. And as a result, we can use some of those ideas to our advantage when we start doing some analysis. Something else to note is that absorbance changes, and in particular increases as concentration increases. So looking at our key, what we can see is as we go through our colors that we are increasing concentration. These are all measurements that are micromolar or micromoles per liter. And what we see is as we increase our concentration, the absorbance increases as well. So using this concept of different substances absorbing different parts of the spectrum, as well as absorbance changes with concentrations, we can use this to construct a calibration curve. So let's say I've been able to figure out that my sample is contaminated with copper, but I don't know what the concentration of the copper contaminant is. What I can do is construct a calibration curve to try and figure that out. And when making the calibration curve, what I'll need to do is make standard solutions of known concentrations with a copper substance. So for example, I might make some copper nitrate solutions. What I'll do with those copper nitrate solutions is make them at different concentrations. What I can then do with that is put one or all of them into the spectrometer and figure out what types of wavelengths are absorbed by copper the best. This diagram here isn't necessarily copper, but let's just for the sake of it pretend that it is. We put our substances in, look at the spectra and see that copper seems to absorb this part of the spectrum best. For simplicity, let's say that that's 550 nanometers. What we can then do is get all of our samples and measure the absorbance of the copper nitrate solutions at a different concentration at 550 nanometers and plot concentration versus absorbance onto a graph. Once all of our data is plotted into the graph, we can then draw a line of best fit, and this can give us an indication of the concentration of any substance based on what absorbance they get in the spectrometer. So an example that I've got here is for a calibration curve that was made for chromium 4. we can use that to figure out the concentration of chromium contaminating a particular sample. So again, you would make up your chromium standards of set concentrations, put them into the spectrometer, figure out what all their absorbances are, and make a calibration curve. And then you would put in your unknown substance. Let's say that the substance got an absorbance of 0.5. What we could then do is plot 0.5 onto the calibration curve and figure out roughly what the concentration would be. Here we can see that it is just over 0.6 milligrams per litre. And that would be a rough estimate for the concentration of chromium that's contaminating our sample. Rather than just trying to extrapolate data by looking at it visually, you could also use a y equals mx plus b formula and solve for x like I've did on the side here to figure out what the concentration is as well, which we found to be 0.63. Another machine that can be used to construct calibration curves and determine the concentration of inorganic substances in a sample is atomic absorption spectroscopy, also known as AAS. It works really similar to UV Vis, but instead of figuring out how much light is being absorbed by the sample in a solution, we instead vaporize the substance, forming ions as gas. We then put light through the sample, seeing how much is actually being absorbed, goes through a monochromator so that we can measure each wavelength at a time and figure out how much of the light is actually being absorbed. In a similar way, we can get different metals or different substances. So here we have a bunch of different kinds of metals showing different absorptions at different wavelengths. Then we're able to construct a calibration curve very similarly to the way that we did before and use that to find the concentration of contaminants in a sample. So they are really similar. There are some differences though with UV Vis and AAS, and it's mostly got to do with the lamps that are used. UV Vis has a lamp that's able to emit a very broad range of visible and UV wavelengths, making it good for measuring a whole range of different kinds of compounds. Whereas with AAS, we use a particular lamp called a hollow cathode lamp. And these are made with different metal electrodes. So for example, if you were trying to measure the concentration of copper in a sample, you'd put in a copper hollow cathode lamp. And what's really special about that is the lamp can emit the exact wavelengths of light that the copper sample is actually going to absorb. And because of that, because you're not trying to emit a wide range of different wavelengths, it actually makes AAS a little bit more accurate. Last thing to keep in mind is the concept of calibration. It's really similar to IR. You generally take a blank measurement first. What that means is the light is passing through the air and whatever air composition you currently have in your lab at the time. It passes through the container that's actually holding the sample, and it will pass through the solvent as well. And that blank measurement will ensure that the machine itself knows exactly how much light can pass through without the substance. And then when it's taking those absorption measures, actually measure the absorbance of the substance and nothing else. Thank you very much, everyone. In the next video, we're going to be spending a little bit of extra time really focusing on the practical applications of what we just discussed today, looking at the steps that are taken to actually make a calibration curve and find the concentration of a contaminant in an environmental sample. But until then, have a good one.